electrical quantities, right? So we actually saw how we can convert the mechanical quantities into the electrical quantities. So we do this previous slide. After that, we converted the mechanical quantities delta m and omega ms to delta and omega s using these two equations. Okay. Then finally we got this final notion of swimming. We say that actually this equation is giving us the information of road acceleration, right? And we also say that whenever we solve these equations, it will be very much difficult for us to handle this second order equation whenever we solve it using some numerical techniques. That's why we split this equation into two first order equations. So this is the first order equation number 1, which gives us the information about the delta, that is the P delta into delta dt equals to omega minus omega s. And then the second equation is this d omega delta dt. It is nothing but the right hand side of the swing equation, that is the omega s. Delta 2 is Pm power unit minus P power. Okay. And then we told that now our focus will be on this parameter, that is the P, the electrical power. Because the other parameters we can easily find it from the problem statement. So this term should be given in the problem statement directly. Like this omega s rule, actually you know the frequency f, then omega s will be simply twice pi f, right? That can be 15 Hz or 60 Hz. Then h is actually the inertia constant, and we know that we can calculate the h using this equation. H is related to this j term, right? So if you know the j term, that is the moment of inertia of the rotating body, and then omega ms can easily find that one from the frequency function. Then hv value will be given, that is the base integral. So subsequently this is value will be known to us. Okay. That means we can easily know this value of h. Then the Pm per unit, the mechanical power input, that value will be given directly in the problem statement. So it should not be our answer. This Pm value. So the only thing that is remaining here, that is the P, the electrical power. Coming to this class, we will see how we can express this P with respect to other some variables. Okay. So today actually we will start from this slide. That is the expression of P. What is P? P is the electrical power. So do you have any confusion up to our first class that we cover up to this slide? If you have any question up to this slide, you can ask. Otherwise, I think we can start our today's discussion from this slide. Omega is actually the synchronous speed, but in the electrical domain. It's this diagram. Okay. So whenever we calculated the theta m and the delta m, we took help of these two rotating two references. One was synchronously rotating and another was stationary. So the speed of the synchronously rotating reference frame was omega m, right? M means the mechanical. Whenever we convert this mechanical quantity to the electrical quantity, it will be simply omega s, right? So this omega s will be actually the electrical speed of the synchronous rotating reference. Also, if the system or if the generator is in the equilibrium state or in the steady state, at that time also this rotor speed will be equal to the omega s. Okay. Obviously, the electrical speed of this omega s. Then if we convert this omega into omega rho, then that omega will be equal to the omega s. Okay. So this is basically synchronous electrical. Yeah, exactly. The synchronous is not. So omega s is the synchronous. Okay. So now I think we can start from this slide. So here we can see that the same system that we discussed in our earlier classes. Okay. So this is the single machine in mechanical system, right? Here we have only one synchronous generator here on this side, and this is our main mechanical system. You know that actually all the parameters in this dash, that is the E prime and X dash. Which type of parameter are actually this element or these are the grounding parameters, right? We actually discuss these things while actually we are actually bothering about only the T dash. This is the transient reactance of the generator, right? This is actually the transient reactance of the generator, but we have drawn it outside this generator to actually make it more clear. Okay. Then this is the VG of the terminal voltage that we get the output side of the generator. Okay. So in the inside, the internal part there is P prime, but whenever there will be some voltage drop across the transient reactance of this generator, then finally we get the VG or the terminal voltage outside of this generator. This is our VG. Okay. Then actually this system is connected to this infinite bus with a load. This is our load impedance. Okay, so this is the load impedance, and there is another thing that is the ZX. Okay, so this is actually the local impedance. Okay. So let's think about one power plant system. Okay, so in a power plant we have one kind of substation, right? So inside the substation there may have some equipment, right? So there may have 2 or 3 houses with some electrical loads. So those loads are actually represented by the local load, the local impedance. Okay, so this is actually the local load that is inside the substation. Okay, and this is the load that actually this load are from the customer side. Okay, so this is actually the customer side. Have you understood these two types of load? One is local load and another is the customer load. Okay, so local load means the equipment that are actually inside the substation. Okay, so to actually maintain those equipments, some amount of electric power should be needed, right? So we can actually consider those equipments as some load. Okay, so these are actually the local load that is represented by this local impedance, and these are actually the load from the customer side. Okay. Then finally, this is connected to the infinite bus. Okay. So we know that the infinite bus voltage is V. Okay. And the associated angle is 0 degree, right? Because we know that we take this infinite bus as our reference. That's why this angle will be taken as 0 degree. And with respect to this value, we will calculate the associated angle with this generator. That is angle delta, right? That is our target. And this local impedance is then connected to the ground terminal. So if we count the node numbers here, there will be 1, 2, 3, 4. There will be 4 nodes. Okay, one node will be the ground node, and there will be 3 other nodes. Okay, this is the 1, 2, and 3. And this ground node is represented by the node 0. So do you have any conclusion in this picture? Right. So now, actually to calculate the PE, okay, PE means the electrical power output at the output side of the generator, right? That is this PE value. Okay, so the PE value, the power that will be injected at the output side of the generator, that will be the PE. Okay, so we want to express this PE with respect to some variables. Okay, so to make our calculation easier, we take help of this current injection model. Okay, so what is the concept of this current injection model? So in this model, actually we are representing all the voltage sources with the current sources. Okay, so we will replace all the voltage sources with the current sources. Okay? You can see here there are 2 voltage sources, right? Here in this generator side, that is the prime. Here it is V. Okay. So this one, this one. There are some voltage here, right? In the infinite bus. So voltage means the source of electrical power or electrical current, right? So in that concept, you can say that this is one kind of source, right? So this voltage source and the voltage source will be actually replaced by 2 current sources. You can see here in this side, the I1 is injecting into this node, and here the I2 is injecting into this node, right? There are 2, and we have somehow eliminated this intermediate node here. Okay, this that was our VG, right? Here, that was another node, another source, right? But here you can see in this picture, actually I have copy and consider this same picture here, so we can discuss from there, right? So we see that there is the BG, right? But there is no BG here because we have done some kind of Y to delta conversion here. Okay. So can you say which type of network is this? Y side. This is actually the Y. This is actually the Y network, right? So this is like this. If you want to consider about the resistance of the impedance, okay, it is like this. Our JHD prime, okay, and it is the ZL, and this is the ZS, right? So it is the Y configuration, right? Or the P configuration, the same thing. So this is the P configuration. If you just bend this two sides, and if you can create some Y shape, then it will be the Y configuration. Okay, the same thing. If you just bend this two sides, then it will be Y. Okay. So Y and P actually are the same thing. Now, actually we can convert this Y configuration to the delta or the pi configuration, right? How? So if I represent this Y configuration to the equivalent pi, it will look like this. Okay, so let me take another pen. So the delta will go, the pi will be like this. So one impedance will be here, right? Another will be between these two. Another will be between these two. Have you understood this thing? This is actually our delta. Understood this thing? Because these black lines can be represented like this. So, same thing. This bar X can be drawn as like this. Okay. So this is the delta configuration, right? You can see it as the pi configuration if you look at this model. How? You can represent this like this as well. Look, this is one thing. Let's say this is another thing. Okay. And this is another, right? But look, this terminal represents the ground terminal, right? If we connect ground at the both side, so it will be the same thing, right? This is the pi configuration that is given here. Any confusion here? Have you understood how actually we can convert this diagram to this? So this is Y or T configuration, and from this side we can make it the equivalent pi or delta. Okay, like this. So let's say this is Z1, this is Z2, this is Z3. Okay. So here in this diagram, this will be Z1, this will be Z2, and this will be Z2. The same thing, right? But here in the Z1, Z2, Z2. If you consider about the delta diagram, then it will be this, and if you consider the pi diagram, then it will be like this. Okay. So here actually the pi diagram has been shown. Okay. So because if you know that these two actually are in the ground, right? So if you just place it like this, then our calculation will be easier. We will see that thing in the next slide. But have you understood how actually this diagram has been converted to this diagram? Any confusion here? Now, can you recall that what will be the value of this Z1? Let's say you know all the three impedance value of the Y configuration, that is Z, XT dash, ZL and ZS. Okay. So what is the value of Z1? Can anyone recall? Y is the conversion divided by all impedance. So we have to say the reverse one. It will be like, look, Z1, okay, I'm writing it here. Z1 will be like this. So there will be two terms. One will be numerator, another will be denominator, right? So in the denominator, we have to take the opposite side. Okay. So for this Z1, which one is the opposite arm or opposite side? ZT dash ZL or ZS? Which one is the opposite? This ZS is actually the opposite. Okay. So we will place it here. ZS. Okay. And in the numerator side, it will be, we will take 2 impedance from here and we will multiply, then plus another 2 multiplication plus another 2 multiplication. Okay. That will be like C xt dash ZL plus G xt dash ZS plus ZL ZS. Have you understood this thing? This is the formula. Okay. How we have written this thing? I am again explaining this thing. This is Z1. Okay. So it will be in the numerator side. It will be we have to take 2 impedance at a time and we have to multiply. Okay. Then plus another 2 multiplication plus another 2. Okay. Like this. So here this J xt dash multiplied by ZL. I have taken it plus. Then plus J xt dash ZS plus ZL ZS. As these 3 terms actually are the summation terms, so the order is not order actually doesn't matter here. That means you can take it fast. Yeah, okay. That will be it actually doesn't matter. And in the denominator side, we have to take the opposite side, opposite arm of the Z1. That will be the ZS. Because with this Z1, actually Z xt dash and ZL we are connected, right? But there is the connection of this ZS and this Z1. That means we can say that this ZS actually is the opposite arm of this Z1. This that will be here. This one. Okay, so let me write about the Z2. Then it will be clear for us. Okay, Z2. Now you say what will be here? If I write the Z2, with the denominator side, it will be the opposite side, opposite arm of ZL. What will be this thing? ZL, right? And in the numerator side, it will be the same thing, right? This same term will be here, right? Let's say I have represented it by, let's say K. Okay, it will be K, right? That one is this thing. Then what will be the Z thing? The opposite arm of Z3 is ZD dash, right? J xt dash and the upper side it will be simply the K, right? Everyone understand this thing? Now look, here this Z1 is represented by this Z12 and this Z2 is Z10 and this is the Z20, right? You can easily understand why this type of naming is here. Because look, this impedance is in between this node 1 and 2, right? That's why it will be the Z1 and this is your ground node or node 0. So it will be the Z10. Actually this is Z20, right? And whenever we have converted from Y to delta, our node 3 has been initiated. Okay. Any confusion there? So this is Z12, this is Z20 and this is Z10, right? This is the impedance. So what is the opposite term of impedance? Impedance, right? That we can represent by the Y, right? So the Y12 means the impedance between the node 1 and node 2. So that will be the opposite of this Z1. So you can write Z12 equals to 1 over Y1, right? Similarly, Z10 equals to 1 over Y10. And this is like this. Okay. Any confusion? Now look, in the next slide, all of these values have been listed here. Y10, Y20 and Y1. Okay. In the last slide, actually this is the Z1 is this one, right? The Z1. This is the Z1. So what will be the Y12? Just the opposite, right? So the ZS will be in the upside and this term, this whole term will be in the denominator side. Look, this is the Y12. That is the ZS divided by this whole term. Okay. And this is Y10, this is Y20. Have you understood this calculation? Okay, any confusion after this? So if I actually summarize the thing that I have discussed up to now, that is in today's class we want to express the PE. Okay. So we have taken this diagram. So we are already familiar with this diagram. This is the single machine infinite bus system, right? So this is infinite bus. This is our synchronous generator. E prime is the internal EMF of this generator, and this JHD dash is the transient reactance of this generator. So after some kind of voltage drop, we will get the DC or the terminal voltage, the output side of the generator. Okay. Then this ZS is the local impedance. This ZL is the load. Okay. That are demanded from the customer side. Okay. And this side is actually the infinite bus. You know that the infinite bus voltage magnitude is E, and the associated angle is 0 degree, and the angle associated with this generator we can term it as delta. Okay. And now we can see that there are 4 nodes. One is the ground node, that is the node number 0, and except this there are another 3 nodes, 1, 2, and 3. Now we want to convert this Y configuration to the delta or Y configuration, like this. Okay. So whenever we did this, this node has been eliminated. Okay. And you can see that there are new 3 impedance value, and you can write the value of these 3 impedance using the Y to delta conversion formula. Okay, that is like this. Then we say that for each line there is the admittance value as well, right? Admittance is the opposite of impedance. So from the impedance value, you can easily calculate the admittance value. Simply 1 over the impedance value, like this. So using that concept, you can write here like this. Y12 is simply it will be like 1 divided by Z12, right? And here in this slide we show that the Z12 means this multiplied by Zs. Okay. So what will be the Y12? It will be Zs multiplied by this term. Okay. Similarly, you can find the Y13 and Y2. Okay. Any question here? Okay. Now look, so this is our current injection model, where actually we have represented the voltage source with the current source. Okay, so we have 2 current sources, I1 and I2. Okay. Now in the next slide, we will write the formula for this current I1. Okay. So can anyone say what will be the I1? What is the I1 here? You know that actually the E equals to I, right? So I means V divided by R, right? Or if I think about the impedance value, which is simply V divided by Z, right? And here all the impedances are actually replaced by admittance. So if I write in terms of admittance, what will be the value? It will be V multiplied by Y, right? V multiplied by Y. So I means V multiplied by 1. Okay, so we will use that concept. So here I1, look. So I1 can be split into these 2 parts, right? Let's say this is I1, this is I1 prime, this is I1 double prime. Okay, so you can write I1 as I1 prime plus I1 double prime. Okay, so what will be the I1 prime? It will be the voltage difference between these 2 nodes multiplied by the admittance. Okay. So what is the voltage difference between these 2 nodes? Here the voltage is E prime, and here it is 0 because this is the ground terminal, right? So we can write I1 prime as E minus 0, and then what will be the admittance here? Y10, right? So this is actually the Y10. Okay. Plus what will be the expression for this I1 double prime? It will be E prime minus V, this V, right? Multiplied by Y1, right? So then, so this is the E prime. So E prime minus V multiplied by Y1. Okay. Now, so if I group them, it will be like this. Let's say here actually this is actually E prime. Okay. Y10 plus E prime Y12 minus E Y1, right? So I can write like this, that if I take common E prime here in this of these two terms will be like y10 plus y12 multiplied by e prime. Okay, minus y12 okay. So have you understood this the final line of this line? So it will be like I1. Okay, any confusion? Here actually this line has been written directly here. Okay, so I1 means y10 plus y12 multiplied by e prime. Okay, minus y12 known as this thing. Good. So with the e prime there is y10 plus y1. y10 plus y1. Then there is minus sign. y12 multiplied by v minus y12 multiplied by v. Okay. So this is the expression for I1. Now similarly, can you find the expression for I2? This is simply, let's say this is I2 double prime. And let's say this is I2. Similar, right? So the I2 will be I2 prime plus I2 double prime. So what will be the I2 prime? It will be the voltage at this node minus the voltage at this node. That will be the V minus 0 multiplied by the admittance value of this branch, right? Or this line. That is the y20 plus what will be the I2 double prime? It will be V minus E prime multiplied by y1. Okay. So if I just again group them like I did actually the previous slide. Okay. So I want to write this in this format. Okay. So all the impedances associated with the E prime will be at one side. Then all the impedances, admittances with the V will be another one. Okay. So if I just write like this, it will be it is actually the V multiplied by y20. Here V multiplied by y12 minus E prime multiplied by y12. Okay. So what is the final expression? Good. Let's keep the V term fast. Okay. So it will be simply y minus y12 E prime here plus y12 plus y20 multiplied by V. Okay. Like this. Any confusion there? I think this is some basic calculation. Now from this equation we can form the matrix, right? This matrix. Yeah. So our unknown parameter is I1 and I2, and that's why we have kept the unknown parameters I1 and I2 to the left side, and the right hand side we have our known parameters. Okay. So you can write like this. So you know the matrix multiplication, right? So if you do the matrix multiplication of this matrix, then it will be simply I1 equals to this term multiplied by this, right? Then plus this term multiplied by this. Okay. So you will simply get that from this original expression, right? That will be this I1. Similarly, if you want to take the I2 will be equal to this term multiplied by this, that is this, okay, plus this term multiplied by this, then we get this. So from this equation we can easily form the matrix. So any confusion here? No, right? We have our matrix. Those who have joined late in this class, actually you have to attend this class with another session if you want to get the activities. Okay. Obviously, you have another class with the same routine, but actually I don't know how we will implement that thing. That will be up to you. Already the attendance has been given, so those who have joined late, please do not request me to give you the attendance. There is how actually we have formed the matrix? No, right? Now, actually this term we have represented by the capital Y11. Okay. Then this term by capital Y1, then Y21, Y22. Okay. Can you give any name for this matrix? This is actually the not actually the coefficient matrix. This is actually the admittance matrix. These all are actually the admittances. Okay. So this is the admittance matrix. So this type of admittance matrix we have formed in your power system properties, in the load flow or power flow section, right? So this is the admittance matrix. Now there are some properties of admittance matrix. Okay. The first property is that all the diagonal element will be same. Okay. Look, these two are called the diagonal element. Okay. Have you understood this thing? Okay. So this matrix thing actually is already taught in our Bangladeshi curriculum, right? So maybe this type of things can be difficult for the foreign students. Okay. So you just focus here. Look. So this diagonal term. Okay. These elements and these elements are called the diagonal elements. Okay. And other elements are called the off diagonal elements. Okay. Off diagonal elements. Okay. And this term is called the diagonal elements. Okay. So this is actually written with the 2 by 2 matrix. Okay. It may have 3 by 3 or 4 by 4. Okay. So let's say if it is 3 by 3 matrix. Let's say 1, 2, 3. Okay, so there will be some admittance values in place of this number. Okay, 7, 8, 9. So in that case, this 1, 5, and 9 will be the diagonal elements. Okay, and the other elements 2, 3, 4, 7, 8, 6 will be the off diagonal elements. Okay. So the first property of the admittance matrix is that the diagonal element will be same. Okay, you can see these two. These two, okay, it will be actually same. Okay. How it will be same? Actually, if we consider that these two are same, okay, then actually it will be same. It is like this. Actually, whenever we do some kind of assumption, then we will see that this y10, then y20 are actually same. But for the time being, let's think that these two are same. At that time, these two will be same. Okay. Then what will be the off diagonal elements? The property says that. Actually I have said the wrong thing. Okay. So I have again said the thing. The off diagonal element will be same. Okay. So the off diagonal elements will be same. Look, these two are the off diagonal elements. Okay. Y0 and Y2. So these two values are actually same. Okay. And how can we write the diagonal elements? So whenever we write the diagonal elements, let's say we are writing for Y11. Okay. So that means this diagonal elements is related to the node number 1. Okay. So we have to take all the admittances that are connected to node number 1. And then we have to sum all of them. Okay. So with this node number 1, we have y12 and y12. So we have to add this two. That will be y12 plus y10. Then for this y22, that is for node number 2, right? What will be that value? It will be simply the admittance that are actually connected to this node. That is y12 plus y20, right? So you can see y20 plus y1. Okay. So you can write like this. If there are 3 by 3 matrix, the concept will be same. The diagonal elements you will get by summing up all the connected admittance with that node. Okay. And the off diagonal elements will be same. But what will be the value of off diagonal elements? Look, for the y12, that means the admittance that is present in between these two nodes, 1 and 2. Okay. So here in between this 1 and 2 we have y12. Then we have to take the minus sign. Okay, that is the thing that you have to remember. We have to take the minus sign. So the admittance in between 1 and 2 is actually y12. And also if I say that the admittance in between 2 and 1, it will be the same thing, right? y12. So that's why these two are actually same, but with a negative sign. So any confusion here? form the admittance matrix, and we have said the two properties of the admittance matrix, that is the top diagonal elements will be in negative sign and their elements will be same, and the diagonal elements you can calculate by summing up all the admittance terms, okay, that are related or connected with that. Now if you do not have any question, you can go to the next slide, that is the last slide of today's discussion. Okay. So here finally now we want to express our real power. Okay. That is the PE. Okay. So PE means the electrical power output. Okay. PE means the power that is actually is integrated here. This P. Okay. Obviously it has two values like this. It will be P dash or P double dash. Okay. So P means the power that is injected into this node. Okay. That is actually you have to understand. Okay. Because P doesn't mean this value or this. P means the electric power output from the generator side. Okay. So that's why the P means associated with this E prime and this I prime. Okay. That is the P. So P is the real power, right? So we know that we have three types of power, like if we form the triangle, power triangle, then actually this term will be the apparent power S, okay, in let's say volt ampere unit, okay. This term will be the P or the real power in watt unit, okay, and this term will be the Q, the reactive power, right, in the VAR unit. Okay. So if you want to establish the relationship, then let's say this is the theta, okay. Then the T will be S cos theta, okay, and Q will be S sin theta, like this, okay. And you can write the S is root over T square plus Q square, okay, like this. So here, whenever we take the P means the real part of this case, okay, because actually we can, here actually all the terms are actually in complex term, okay, all the terms can be complex. So in the complex domain, if you want to actually represent this thing in a rectangular format, it will be like this. This will be P plus JQ, okay. This will be like this. That's why the magnitude of S is root over P square plus Q square. Okay. So P is the real part of the S, and Q is the imaginary part of the S, or the apparent power. Okay. And S means the multiplication of voltage and current. Okay. Voltage and current, but not actually the current. Voltage and the current conjugate. Okay. I think you should know that concept. That how can you actually determine the apparent power or the S? It will be the voltage multiplied by the conjugate of the current. Okay. Complex power actually is the apparent power. Yeah, exactly. So you can see how can we calculate the P? P will be the real part of this complex power. Okay. Complex power means voltage multiplied by the conjugate of current. What is the voltage here? Is E prime, and the current is
double prime P. Does it subtractive here or is it a branch?
not actually. This is, we can write it like P1 and P2. Okay, then I think the option is this is not double prime. Doesn't mean the sub transient like this. Okay, so I am just saying that this P can be split into two blocks. Okay, this P1, this P2 like this. Okay, so what will be the P? P will be the real part of this thing. Okay, so here we should know that here all the terms E prime, then V, and all the admittances as well are in the phasor form, okay, or are in the complex form. That means if I want to represent the E prime, so E prime has both its magnitude, that is the modulus of E prime, and the associated angle, that is delta. Okay. If I write about the V or the voltage at infinite bus, it will be the magnitude of V, and as we are taking the infinite bus as our reference, here the angle will be S0. Okay. Then for the admittance y11, it will be simply the magnitude of y11, and let's say the angle associated with this is theta 11. Okay. Then for y12, it will be the magnitude of y12, then theta 1. Okay. Which means 4 things are needed. That's why I have written these 4 things. But similarly, for y22, it will be the magnitude of y22, angle theta 22, like this. Okay. So look, the real part of E prime and then the multiplication of the conjugate of this I1. So how can we represent this E prime? With this term, the magnitude and the angle. Okay. Then what is I1 conjugate? We know the I1 term, right? This is the I1 term. Okay. Yeah. Okay. I am saying that one. Look. So this is the I1 term. Okay. So actually from this thing, this is the final version of our I1 and I2. So from this thing we can write like I1 will be equal to y11 E prime then plus y12 V. Okay, like this. Have you understood this thing? So instead of writing like this, because this is represented by y11 and with this minus sign, this is represented by y1. So simply this is actually the I1 equals to y11 E prime plus y12 V. Okay. Now what will be the I1 conjugate? Okay. The conjugate means, let's say we have I1 as I1 magnitude multiplied by, let's say, theta 1 in phasor form. So what will be the I1 magnitude? And we must say I1 conjugate. Only the angle will be the opposite, right? And the magnitude will be same. That means it will be magnitude of I1. Then only there will be one minus sign there, right? If it is minus, then it will be plus. If it is plus, it will be minus, like this. Okay. So here we know that our I1 means y11 E prime plus y12 V, right? So what will be the I1 conjugate? We have to just take the minus, okay, minus sign in each side, right? Good. Yeah, okay. So this whole term is actually the I1 conjugate. Okay. First term is the y11. So we have written the magnitude of y11 and the angle was theta 11. But why minus sign? Due to the conjugation, right? So minus theta 11. Then this E prime. So magnitude of E prime and minus delta, right? And then plus y12. So plus magnitude of y12. And the angle was theta 12, but due to the conjugation it will be minus. Then V magnitude multiplied by the 0. 0 and minus 0 are actually the same. Okay. And that's why it is written by 0. You can write minus 0. Okay. So have you understood this thing? So after that there are actually 4 to 5 lines, but these lines has been written directly. Okay. So how can you actually calculate this thing that actually I can show in the board? Okay. The market is working properly. Okay. You can see that I am showing it here. Here all in this term. Okay. In this term, you can just add these two together, right? The angle value can be added, right? So it will be like magnitude of y11 multiplied by E prime angle minus delta minus theta 1, right? Theta 1 like this. And plus here it will be y12 multiplied by V. Then what will be the angle? It will be simply minus theta 1. Okay. So actually I think I have to write it here. This like real part of another term, right? But these both terms should be multiplied with this term, right? So this is the first side. So if you take this and this, okay, multiplication, then it will be to plus delta minus delta. Okay. So this delta will be vanished. So will be only the real part of the magnitude of this and this will be the square, right? So it will be like e prime square, then y11, then this 3 angle will be simply minus theta 11. Okay, have you understood this thing? Which is multiplied by this first term. So these two magnitudes are getting square, and these 3 angles have been added, and finally we have got the minus theta 1. Then plus it will be magnitude of e prime, magnitude of this b, then magnitude of, let's say, y1. Okay, and what will be the angle? It will be simply this delta minus theta 1, right? Delta minus theta 1. So do we have any confusion here? No, right? Now let's say we have to take only the real term, right? So let's say we have this thing, let's say a magnitude of theta, okay? Let's say this is actually the a value. A in complex, it can be represented by the magnitude of a, and the, let's say the associated angle is theta, okay? So this is in the polar form, right? If we want to express it in rectangular form, in the Cartesian form, what will be the expression? It will be simply the a cos theta. A means the magnitude of a, right? A cos theta plus j a sin theta, like this, right? So you know this thing. Maybe you have studied it with this r done, right? So r angle theta means r sin theta plus j r cos theta plus j r sin theta, like this, right? Now our target is to only take the real part, okay? So if you want to take the real part, this is the real part and this is the imaginary part, right? So we will ignore this part completely and we will only take this part, okay? So just if I only extract the real part, what will be the real part for this? It will be simply e prime square y11, then it will be cos, right? Cosine of minus theta 1, right? Then the next term it will be this multiplied by cosine of delta minus theta 1. Okay, so have you understood this thing? And we know that the cos minus theta means the cos theta, right? This is the simple trigonometric rule. So you can write like cos theta 1. Okay, so this is the final line. You can see that it is actually the magnitude of e prime whole square, magnitude of y11 and cos theta 11. Okay, plus magnitude of e prime, magnitude of e, magnitude of y12 and cos theta minus delta minus theta. Okay, because we have taken only the real part, we have neglected the imaginary part. Okay, any confusion after this? Now we have to do one kind of assumption, that is, let's say our circuit is purely inductive circuit. Right? What is another term with the inductive term? That is the resistive term, right? We have neglected the resistive term because we want the power loss as minimum as possible, right? To minimize the power loss, our resistance value should be less, right? Or should be minimum. That's why we have assumed that there is no resistance value to get rid of from the power loss. Okay, that means whatever power that will be supplied from the generation side, the same amount of power should be delivered at the any side. Okay, so that is the thing. That's why we have assumed that there is no resistance in our circuit. So our circuit is purely inductive circuit. So for purely inductive circuit, what is the value of theta? 90 degree. Because in the purely inductive circuit, the current lags voltage by exactly 90 degree, right? So that's why we can term this theta 11 and theta 22 as the 90 degree you understood this thing? Then what will be the y value? You know that we can write this j with the resistance plus jx or the reactance, right? The opposite of this y is z is y. Okay. So how can we represent this y? It will be, can you not say? Here instead of this r term we should write actually g. What is the opposite of r? The conductance g, right? And here this is b, the susceptance. That is the opposite of this reactance, right? So this is the term for the y and this is the z. Okay. So as there is no resistance, so there will be no, actually we can omit this conductance. Okay. So actually this will be simply y12 equals to b12. That will be simply the opposite of this reactance. So we can write 1 over next one. Okay. So now in this formula, cos 90 is 0, right? So this term will be vanished because this cos 90 will be now 0. And here it will be like cos delta minus 90 degree because this theta 12 is also 90 degree. So cos delta minus 90 will be simply sin delta, right? And here we have this e prime, then v, and this y12 we can write it as 1 over x1. Okay. The final form of this p will be modulus of e prime multiplied by the modulus of p sin delta divided by x1. Okay. So what is x12? X12 is actually the reactance in between node 1 and 2. Okay. And this is called the transfer reactance. Another term is transfer reactance, or the reactance in between node 1 and node 2. Okay. That is the x1. What is the magnitude of E prime? E prime is the generator induced EMF, the internal EMF, right? That is the E prime. What is the V? V is the voltage at the infinite percent. Okay. And what is the delta? Delta is the angle associated with this E prime, right? That is the delta. So if we know this values, we can find the P. Okay. P is this thing. So we have finally derived the expression of this P with respect to E prime, V and delta. Okay. Any question here? Because we have assumed that there is no resistance in our circuit. Okay. So our circuit will be purely inductive. Okay. So it is the theta 11, theta 12 represented by. Any other question?
Transfer reactance.
X12 means the transfer reactance. So the reactance in between node 1 and node 2 is X12. That is here. The reactance here. Node 1 and node 2. Class, we will see that how actually P value varies with respect to delta. Okay, you will see this kind of graph. So I think today